Well, with each example, I try to unfold just one additional layer of this concept of double integrals, and in particular now the polar version of the double integral. And we're going to look at an example again to sort of unveil this other concept. We're going to spend a little bit more energy just investigating theta. If you take a trigonometry class in the West, you kind of think of there's no such thing as angle values different than pi over 6, pi over 4, pi over 3, pi over 2. And we know simply that is just not the case. So take a region that's bounded by the line y equals negative 3x, the horizontal line y equals 6, and that's right, that's the y-axis. So visually, we are studying this region here. So that's 6 units up. This is the line y equals negative 3x. The y-axis is x is 0. And when we investigate this, we have to set up our integration. We would need boundaries for both r and for theta. Well, the r part of the boundary is from the origin well, 6 units here, but more than 6 units there, and even more than that, up to whatever that distance is. And because that radius is changing, there's likely to be a variable there. So I'm just going to write y equals 6 as a placeholder, because that's the name of that boundary in my xy language. So the origin would be the same as r equals 0. But y equals 6 could be rewritten. R sine theta is 6. So r equals 6 divided by sine of theta, or 6 multiplied by cosecant of theta. So 6 cosecant theta. Now theta is varying from this 90-degree pi over 2 to whatever that angle is there. So theta is at pi over 2 to whatever that angle becomes. Theta equals pi over 2 to theta equals, and this is what I want to look at in this little video segment. So I can tell you now it's not going to be a multiple of pi over 4, pi over 6, or pi over 3. So I want to see what we can do with the tools that we are supposed to have. So let me slide down here and slide up here. And we're going to look at this visually from our old triangle trigonometry days. This is 6 right here. And I didn't take the time to measure this before, but if this line's equation is y equals negative 3x, then x would have to be a negative 2 in order for this to be a positive 6. And we know that x squared plus y squared is equal to r squared. And so 6 squared plus negative 2 squared equals r squared. R is going to be the square root of 40, or 2 root 10, or a decimal value that your engineering application might require you to use, or your physics application might require you to use. So I'm just going to write in here square root of 40. So let me just take a little tour through our 3 basic trigonometry functions that we might utilize with the calculator. First, sine of theta is equal to y over r, 6 over square root of 40. In that case, theta would become the inverse sine of 6 over root 40. The cosine of theta is x over r, negative 2 over root 40. And so theta is the inverse cosine of negative 2 over root 40. Finally, the tangent of theta is y over x, 6 over negative 2, which is negative 3. So therefore, theta is the inverse tangent of negative 3. Now, if you were to go to your calculator, and I'm going to suggest degree mode for just purposes of comparison, you will find that only one of these three will provide you the angle in quadrant 2. Maybe it's a fact that we should know from our trigonometry days or pre-calculus days, but it's likely not a skill you've exercised as often as it could be exercised. The only value that works here, is the inverse cosine of negative 2 over root 40. To use one of the remaining two choices, you would have to perform a couple of other arithmetic operations in order to utilize them. So when I go to my polar integral, if I'm just interested in looking at the area of that region here, r dr d theta, r went from, you have to go back to the beginning, theta and r went from 0 to 6 cosecant of theta. Theta goes from pi divided by 2, or pi halves, to inverse cosine of negative 2 over root 40. That is probably not easy to see. Inverse cosine of negative 2 over root 40. Pi over 2 to that represents the 90 degrees to whatever that angle is past 90 degrees. And 0 to 6 cosecant represents from the origin to the horizontal line. So this triangle here. All right, theta, don't underestimate it.